All right, are you ready for section 2.5, scatter plots and lines of regression? I hope so. Let's get started. The first part will just be going over vocabulary, some of it which you may know and some of it which may be new. So the first thing we have is bivariate data. And what this means is data sets with two variables. And if you recall, bi, like bicycle and so forth, means two. So bivariate data, we're comparing two sets of variables, x and y. Are the most common variables, of course, used. So what is a scatter plot? A scatter plot, which is also known as a dot plot, is a set of bivariate data graphed as ordered pairs. So we're comparing our x-axis versus our y-axis, okay? We might be comparing temperature over time, height versus weight, but two sets of data will be plotted on our coordinate plane. A line of best fit is a line that closely approximates the data. So our dots from that scatter plot hopefully will trend in some sort of direction, and a line that passes through them that represents the data well is a line of best fit. Our prediction equation is an equation that we come up with based upon points of the line of best fit. And once we have that equation, we can predict other data from that set. Lastly, we have correlation. As mentioned, hopefully the variables have some correlation, but they may not. So if we look below at these charts here, our first example of our dot plot or our scatter plot shows positive correlation because when I draw a line of best fit, this red line, we can see that it's trending up. It has a positive slope, so it has a positive correlation. It also, in this case, has a very strong positive correlation because if you notice, the dots are very close to this red line. We don't have dots randomly scattered about. Most of them are very closely tied to that red line. Then we could have negative correlation. Negative correlation means the data is trending down and has a negative slope. This has a weaker correlation in terms of this exact dot plot, okay? We could have strong negative or weak negative. In this case, it's weaker because the dots are scattered a little further from that line of best fit. If they were all really tightly packed to the red line, we'd have a strong negative correlation. And lastly, we may have no correlation at all. Our dots are all over the place. For example, maybe we have the age of somebody and how many miles they walked that day. There could be no correlation. We could have a young baby who walks no miles and a very old person who walks no miles. We could have a 40-year-old that walks 5 miles and a 40-year-old that walks 0 miles. So maybe there's no correlation at all. Okay. Then we have a regression line. Our regression line is like our line of best fit. However, this comes from the calculator. So oftentimes, graphing calculators or spreadsheets can compute the calculations for the line of best fit, and we call that specifically the regression line. Correlation coefficients are part of that data that we get with the regression line, hence R. If R is greater than or equal to -1 and less than or equal to 1, then it shows us a measure of how well that data is modeled as a linear equation. So, of course, if it's closer to -1, that means we have a negative correlation. And if it's closer to +1, that has a positive correlation. If it's 0, there would be no correlation at all. So let's take a look at some of these examples. Notice if it's 1, we have an exact positive linear equation with the slope of 1. 0.8 is pretty close, so we can see that's a pretty strong correlation. The dots are all pretty tightly packed together. On our third example, we can still see that we are trending up, but the dots are scattered quite a bit. So that's not as strong. It's very low. It's getting closer to 0 where there would be no correlation at all. -0.3, we can see the data starts to trend down, but again, those dots are not compacted tightly together. They're still scattered a bit, so the correlation isn't very strong. Our next one of -0.8, those dots are very packed together, and we're getting very close to that -1 for a complete negative line, which we can see here. We have a slope of -1. So you want to be familiar with our correlations, the types of correlations, and then that R value to understand how strong correlation we may have. Okay, let's actually get started into some practice problems. So the first one we have is to identify the data sets as having positive, negative, or no correlation. For example A, it says the number of hours a person has driven and the number of miles driven. So let's think about that. What happens as one of these goes up? What happens to the other? Does it go up? Does it go down? Or do they really not have any relationship at all? So as the hours increase, the longer we drive, the number of miles also increases, right? So if this increases, then this one increases. So what does that mean? That means we're going to have a positive correlation. Okay, so the hours were driven, the number of miles, they both increase, so we're positive. You try B and C. Think about what happens. So for example, B, the number of siblings a student has. So if we think about that as the increase of siblings, does that mean we increase in our grade? If we increase in siblings, does it decrease in our grade? Or does it matter at all? So think about B and C and try to determine whether it would be positive correlation, negative correlation, or no correlation at all. Okay, let's look at number 2. Number 2 says, use the scatter plot below to answer the following question. So as we can see here, our x-axis is the number of ticket writers. Our y-axis is the number of tickets, and this is talking about traffic tickets. So this makes sense that we'd have positive correlation, right? The more people that are out there to write tickets, probably the more tickets will actually be issued. So we can see we have some positive correlation. Okay, so the police department tracked the number of ticket writers and number of tickets issued for the past 8 weeks. The scatter plot shows the results. Based on the scatter plot, which statement is true? So more ticket writers resulted in fewer tickets issued. So the more ticket writers there were, actually the more, right? So this one should say more. So no good. There were 50 tickets issued every week. So number of, that's not true, right? We have, these are in hundreds, but we have about 400 and so forth. Here, this one is closer to 500, so that one's incorrect. C, when there are 10 ticket writers, so here's my 10 ticket writers, there will be 800 tickets. So let's see, at 10 ticket writers, we're at about a little over 600. So that wouldn't be true. D, more ticket writers results in more tickets issued. So more ticket writers, as we increase, yes, the tickets increased as well. So D would be my answer. Okay, let's look at number 3. Number 3 says, given this scatter plot, answer the following questions. So A says, what type of correlation does the graph have? So if we look at that, what can we see? What's happening? It is overall increasing. So we have positive correlation. Describe the meaning of that correlation. So what that's saying is that the number of hours studying increases, then test scores increase. Hopefully, this data would be true for you all as well. So as the number of hours studying increases, those test scores are increasing as well. Okay, now we want to draw a line of best fit. So let's talk about this. Here you want to be pretty specific. You want to make sure that your line is passing through at least 2 points, okay? So make sure it is passing through at least 2 points. Now, you also want to make sure that those are good points. So what do I mean by that? So if we take an example, okay, and I say, let's pass our line so that it looks like this. Here's a point, and here's a point. I'm going to draw a line through those. Would that line represent my data well? No, it would not. So let's get rid of that. That would not represent my data well. What about if I had this point, and this point? Would that represent my data well? Nope, it's passing through 2 points and almost looks like it's passing through 4 points. But no, that is not trending with those green points very well. So what we want to make sure to do is that we pick points so that the line is pretty much in the middle of the points that we have here, okay? And we want to have as strong as correlation as possible. So for example, we can see that the data is trending upwards, and a line about in here would give me a good estimate. So maybe I could pick this point and this point. And if I draw, you'll want to use a straight edge for sure. But if I draw a line of best fit, I apologize, it's a little tricky with the tablet. If I draw a line of best fit through those points, you can see, as straight as that can be, you can see that not only is it trending up, but we have that line in the middle or so of most of this data. There's a variety of green points to the left, and there's a variety of green points to the right. So those would be pretty solid points. So what we need to do is we need to pick out those 2 points. So this point here was about maybe 962. And this point over here was about 2388. Okay, so again, we drew our line of best fit so that it represents the data well, and then we take those 2 points from that line of best fit so that we can write our prediction equation. Once I have those 2 points, then we can write an equation. We can find our slope and we can find our y-intercept. So let's start by finding our slope. We would do y2 minus y1 over x2 minus x1. So this would give me 88 minus 62 is 26, and 23 minus 9 is 14. If I reduce that, this would give me 13 over 7. So there's my slope, and if you want to approximate it just as like a check, you can do so, and that's about 1.85, give or take. So if we look here, we want our slope to be a little less than 2. So let's think about that, right? These are going by 5s and 10s. So if we went up 10 and over 5, that would be about 2. So is that kind of what's happening? And if we look here, right, if I'm at this point here, I'd go up 10 and over 5. Yeah, that does make sense. So this is a pretty good approximation. Now, you may have picked some points and your slope may have been a little over 2. Well, that's okay. We should all be within the same range. If your slope was 10, then we have a problem. If your slope was 1/3, again, maybe we have a problem. And we certainly have a problem if your slope is negative, because we can see we have a positive correlation. So always just double check, okay? Now that we have our slope, we want to figure out our y-intercept. So we have our equation, y equals mx plus b, and I plug in a y value. I'm just going to use the smaller numbers. 62 equals my slope. I'm going to use the fraction. Our x value is 9. And then we have plus b. So at this point here, this would give us 62 equals 117 over 7. I'm going to make 62 into sevenths. So this would become 434 over 7. Now I can subtract the 117, and that gives me 317 over 7 equals b. Let's approximate that though. 317 over 7 gives me about 45.2. Let's check. That b value is my y-intercept. What's happening here? Is that a good approximation? Well, if I look at my blue line, which is a little crooked, and I keep coming down, yeah, it looks like mine, if I extended that blue line actually straight, it looks like it'd cross around 48, 49. 45.2 is really close to that. So this is a good approximation. If your y-intercept is 70, then something went wrong up here. You picked some incorrect points because 70 would not be a good representation of my y-intercept. As this data trends down, it looks like the y-intercept would be somewhere between 40 and mid-50s. Hopefully that makes sense. So with that being said, one example of my prediction equation is now y equals, my m is 13 over 7, mx plus b. Again, we won't all have the exact same prediction equation, but they should all be similar. So all the slopes should be around the same and all the y-intercepts should be around the same. Okay, let's move on now to number 4. I'm going to start this one with you and have you finish it. So here is a bunch of data. What you're going to do is you're going to actually make a scatter plot. So what we have here is a history teacher asked her students how many hours of sleep they had the night before a test. The data below shows the number of hours slept and their test score. So remember when we have a chart like this, the top one will represent our x and the bottom will represent our y. So when we are labeling our x and y axis, we know what goes where. So if I look at my hours slept, they're really just going by ones. So I'm going to make sure that my x-axis is just going by ones. My y values range from the 60s to in the 90s. So I'm probably going to count that by by tens. Depending upon your data and the graph paper that you have, you can choose the interval that would be best for you. Clearly, we don't want to count by ones. Counting by fives may have been okay, but I think I would have fallen off the graph. So you'd want to have other graph paper for that, but it would be more specific because it's counting by fives. If we counted by 20s, that really wouldn't show a good range. Okay, so now we'll keep labeling. This is my hours slept. And in parentheses, that's hours. And on the right-hand side, this is test score. And we could just say grade. Okay. So now what you're going to do is you're actually going to go ahead and plot. So let's do a couple of those together. So 883. So here's 8, and 83 is a little over the 80 mark. 786. So 7 and 86 is a little over the midway. 774. And we'll keep on plotting. So I'm going to ask you to finish plotting all of the data. Once you have those points, what I'd like you to do is draw a line of best fit. So you'll have all your dots. Pick a line that passes through at least 2 points and that trends with the data well. Okay, if it's increasing, make sure that line is increasing. If the data is decreasing, make sure your line is decreasing. And then always double check that y-intercept that you get. Your y-intercept that you get with your calculations should be the y trend with the y-intercept that would happen when we cross. Okay, so plot the points, draw yourself a line of best fit, make sure 2 points are on it, and use those points, just like we did in the previous example, to create a prediction equation. Once you have that prediction equation, I want you to use it to determine what the score might be if they got 10 hours of sleep. So what does this mean? This means you will plug 10 in for x, because hours is our x-axis, and solve for y. Again, the answer that you get here should match well to your prediction equation. So if we have our prediction equation, we go to the 10-hour mark, wherever your line is, that 10 hours should be about close to that point. Okay? So use that previous example of number 3 to help you finish number 4. A great rest of your day.